per polynomial. Oh, okay. Recording just started. So with this appetizer, I want to rapidly show you what we want to talk about. Now, these values of the Poincaré polynomial for triply graded Kovanov-Rosansky homology, the way I'm going to write them down is going to be renormalized. So there are several ways of writing them down. The essence is all there. But for instance, Matt Ogenkamp in his talk would use capital Q, capital T, and capital A. So if you want to connect to Matt's talk, read everything with capital letters for the Q, T, and A. Also, there's a monomial that multiply all of this when you actually want to describe this super polynomial PPTGKRH. But I want to, I got rid of this monomial that multiply everything here. And also Q and T in the original, they're also use lowercase q and lowercase t. They are differently renormalized, but it's important to do it the way that I'm doing it now for what I want to say. So that's the P and K, the polynomial, for the trefoil knot. So it's Q plus T plus A. And the plan of all that we're going to do today, and maybe for a while, is to try to understand how you can describe these polynomials in Q, T, and A. How you can calculate them directly without going through the actual Kovanov-Rosansky homology calculation. But how you can get formulas that will express these. Now, it's been conjectured and shown recently that these polynomials are symmetric in QT. So if you exchange the role in of Q and T, you're supposed to see the same expressions. So that's the trefoil. And here I've put, so these are the NK torus knots. So you go like this around the torus, number of times you go around like this and like this. That's the N of the K. And you can switch N and K. It's easy to prove that the order in which you put these two doesn't matter. So I'll put the smaller one first here. So let me ask you a question or propose a project. How can we recognize that one of these polynomials is correct? Say I don't tell you how I got a polynomial in Q, T, and A. When is it correct? When does it occur as the Poincaré polynomial of triply graded Kovanov-Rosansky homology? We expect this to be symmetric in Q and T, and there's some behavior about this. And being from algebraic combinatorics, one of our reflexes is to say, can we understand the structure of what is occurring here? And so that's part of our story. Now, the other thing is, I mentioned that this is symmetric in QT, but it's not symmetric in a trivial way. So there's more structure than just symmetry. So here, just look at this. This is all monomial of degree 3. It's the sum of all monomials of degree 3. So it's not only symmetric, but it has this property. This is the same, all monomials of degree 2, and here all monomials of degree 1. And you see something similar here with what happens here. So so if you go further and you look at all cases with 2 and say 2 to the n minus 1, I just want these to be coprime just to simplify today. Then this pattern that you see here keeps on. So you get the sum of all power of monomials of a given degree n being this exponent of 2 here, and then you get the same with n minus 1. So all of these p and k have the same structure, and now I've used a notation here, S and Qt. Sn stands for Schur function indexed by n, and I'll explain why it should be like this in the sequel. So Schur function, I won't define in general, but I'll remind you 2 cases. So there's the Schur function are indexed by partition of integers. Here it's a partition with only one part, and SNQT is just this sum of all monomials of degree n. If you have 2 parts, SAB of Qt, it's a similar formula. You start with A is larger than B here. You start with Q to the A, T to the B, and go all the way to Q to the B, T to the A by lowering the exponents of Q and raising the exponents of T. So all of these guys have the same total degree, but if you sum up the exponents, it's A plus B, for instance. So that's a special case of a Schur function in general, and these will play a role in what we are going to see. And again, this is just a scoop about what we're going to see later, but if you do the same for 3 something, 3, 4, 3, 5, 3, 6, no, not 3, 6 yet, but 3, 7, blah, blah, blah. And you should write here expression in Qt, but they're going to become larger and larger and larger, and you'd like to have some way to make them presentable and almost even memorable, so that you can. I have a bad memory. I never know. So if I have some way of understanding the structure, then it helps me remember. So here, S3 is the sum of all the monomials of degree 3. That's going to contribute for 4 terms in Qt. And S11 is a special case of this AB rule that I showed you just a little while ago. And so you get only Qt. So in total here, in this expression, you have 5 terms in Qt. And if you saw Matt Hogenkamp talk, he gave these 5 terms. Now, if you go on to the next guy here, so this is will contribute 3 terms, Q squared plus Qt plus T squared, and this is Q plus T. So yet again, you have 5 terms here in Qt, but this makes it more compact. And also it exhibits a feature that in general, I don't know how to prove, but I know how to prove it in some context, that these expressions will always be Schur positive. And behind this, there's in the cases where I can prove it, there's an action of GL2, not SL2, not to mix things with other subjects in this area, not SL2, but GL2. And these are irreducible characters. So that's why they occur with positive multiplicities. And then you have the powers of A that go increasingly here. And I'm gonna, I'll show you a bigger example. So when I say we'd like to understand the structure, we'd like to understand what is here, what is here, and what is here, and maybe even how you can relate these three coefficients, for instance. So let's pick a bigger example. So that's P311. And also, by the way, what I'm going to, some of this in the QT world has been described already by conjecturally at some point and afterwards, but this Schur function structure I didn't see. Anyway.
Sorry to interrupt. There's a question in the chat. So Olivier asks if it's always multiplicity free.
No. There'll be 2s and 3s and all that. This is just because the numbers are too small. So it's going to become more multiplicities. And yeah, there's lots of interesting things to say. But so this is just observation for the moment. So you just calculate, and then we will try to understand more. But if you look at this guy, then you wonder, what's the structure of this? That's one of the questions we should address. And also, I'm going to tell you in a minute that, in a sense, this and this is already sitting inside here, if you know what to do. Now, the reason, the title of what our group is as Macdonald polynomial in it. The reason for Macdonald polynomial in relation to what I'm talking to you about now is this formula here. So Macdonald polynomials, I will describe them and explain everything that's mentioned here. They are symmetric functions with when you expand them into the Schur function, that won't be these Schur function, by the way, it will be others. Macdonald polynomial expand our symmetric function in variables x1, x2, x3 up to infinity, using infinitely many variable is a simplifying device. Even computer-like better symmetric function in infinitely many variable. I'll explain why in a minute. But and nabla here is an operator for which these Macdonald polynomial will be eigenfunctions. So we coin the word eigenoperator because Macdonald polynomial are eigenfunctions and eigenvalues I'll explain later. So there is an operator like this that we have to describe. So that's the purpose of today, in a sense. Describe this operator, apply it k times to E3, and then this is a symmetric function. By the way, E3 is the elementary symmetric function. In terms of Schur function, no, I didn't. Elementary symmetric function anyway. So you apply nabla ek to the elementary symmetric function. The Q and T, they appear because of this operator. E3 doesn't have Q and T in it. And then after applying the operator, you get a combination of symmetric function, and you take the scalar product. That means take the coefficient of E3 and this. Now, if you do that, you get the zero the part with no a's, when I stick a equal to 0. So the blue rectangle here is this expression when you set k equal to 3. No, that's wrong. Yeah. Oh, yeah, I didn't take the same. So I have to explain. I would have to write another formula for this. So that's not an example that meshes with this, but let's not do that now. Anyway, so our picture maybe is like this. I've been showing you these PPTGKRH polynomial, the super polynomial. When you specialize Q and T, you get something, the Jones polynomial, or if you specialize other ways, you get other classical polynomial not invariants. These also are polynomial not invariants, but at a slightly higher level. And Khovanov homology is a categorification. So here you have the arrow of categorification. And in between, the categorification of the Jones polynomial that correspond to Khovanov homology or triply graded Khovanov homology, they're symmetric function. And I think it's worth talking more about this level. This is above this. At this moment, it's just a translation, but there's something more to say. And on the other side, this Hilbert scheme also is related to this. So that's the reason why we have everything, and the McDonald polynomial are going to be involved in going like this. So what are McDonald polynomial? So the Schur functions are a basis of symmetric function. I'm going to assume that there's infinitely many variables, because otherwise I have to say it's a basis if you restrict to partition that are have some limits on either the number of parts or another basis, so the size of the parts. So there are special cases, and we don't like special cases. So if you don't want to have to care about special cases, you put infinitely many variables. And now the next step is not to write down the variable, but just to write down S mu. So the S mu here is actually S mu of X. But most of the time, it's a good idea not to write the variables. And all calculations are done in a way where you don't need to write down the variables. If you don't, then the computer is very happy, because he is going to do calculation with abstract S mu and do everything like this. And if you put variables in, then these expressions become huge expression if you have too many variables. And anyway, so it's much simpler not to write down variables. So, but each of these green S's, they are polynomials. Let me say something that I shouldn't say. Polynomials in infinitely many variables. But now that's why we all sometimes call them functions. It's not actually because they're complicated. It's just because they're inverse limit of polynomial. So you have infinitely many variables in the polynomials. So whenever I use a symmetric function in the sequel, it means actually polynomial if you would restrict the number of variables to be finite. Now, yeah. So I'm being a bit, for some people here, I'm not actually saying how to define the Schur functions. Let me consider them as basic blocks in the notes. There are actual descriptions, but what's really important is not what they are in detail, but how but the fact that they also form a basis of symmetric function if I consider partitions of a given size. So partitions are, that's partitions. A partition of n is a way of writing n as a sum of positive integers. So mu is mu1, mu2, up to mu k, a list of positive integers. And you suppose that these integers, they're written in a decreasing order because you want to write n as a sum of these, and the way some commute. So anyway, and the typical way of representing to give a representation of these partitions is just to write rows of length. So I should use a yellow color: mu1, mu2, mu3, mu4, and mu5. These are the parts of the partition, and the length, the size of the part is the length of the row. So that would be a partition of one with the total number of all squares here is n, and mu1 is the number of squares in first row, mu2 second row, etc. Now, this is the diagram of the partition, and typically we don't, I'll use the same notation for the diagram as for the partition. And the context typically takes care of telling you what's correct. So that's a partition here. And now that it's as a representation, geometrical representation, as a bunch of little squares, each little square like this, I'll call a cell, and it's going to have a coordinate given by the southwest corner here. So that's coordinate ij. And by the way, I draw my diagram in the French way. I think most people in our group that work on Macdonald polynomial, they use the French notation. The English notation is easy to get. You just flip, look at this in the mirror upside down like this, and then it's an easy exercise to do, but then you get the English notation. But here, what's useful is that a cell, the coordinate of a cell is the Cartesian coordinate of a cell. So it's something we're used to. So the partitions are going to index both Macdonald polynomials and Schur function. Both, if I consider a symmetric function that are homogeneous of degree n, then Schur function indexed by partition of size n form a basis of that linear space, and Macdonald polynomial also. So here you have the change of basis between Macdonald and Schur. No definition yet, although this is a definition of the H3, H21, H111, but I've not told you yet what's the rule to put these coefficients. Now, some of you might want, if you're new to the subject, you will wonder of why there is a tilde at the top here. The tilde comes from the fact that at some point in the history of the subject, there was another family of Macdonald polynomial like this without the tilde. They're closely related to this, and the untilde version, the Q cube here, would be here. So you would exchange, there's some flip of this. Likewise, the QT would be here at the beginning. But it became clear rapidly that this was a better convention, to put it this way, for representation theory reasons, at least. So a tilde was added to the notation, and it's been there for 25 years at least. And the other untilde version is almost never used. So but it's hard to get rid of the tilde. Anyway, so that's the Macdonald polynomial H3, H21, H111. H3 does not have T in it. H111 does not have Q in it. But because these are like extreme cases, but here you have QT. So the underlying field is the rational fraction in QT here. And it took a long time to be able to prove that the coefficients here were actually polynomials with positive integer coefficient, but now it's been shown. So these are the Macdonald polynomial instances. Now, in what we're going to do, there are going to be some eigenvalues, special eigenvalues will play a role. So eigenvalues we'll consider operators on these polynomial, and with these will be eigenfunctions of these operators, and we will have interesting operators having interesting eigenvalues. Now, here are two examples of such eigenvalue. So you have a partition. There are the cells in the partition. You consider all cells and calculate Q to the I, T to the J, and multiply all of this. That's one eigenvalue that will be very interesting. We're used to calling T mu of QT. And another eigenvalue that is interesting is just a similar expression, but with a sum instead of product. Before I leave this slide, another parameter will play a role in, other parameters will play a role in our story. So if you have a cell, you can look at all the cells that sit to the right of it on the same row. I drew it here like this, but if I would have more cells sitting up here, they wouldn't be involved in what I'm trying to describe now. So you have a cell in yellow, and in blue, you have cells that are on the same row to the right of it. The set of all these cells is called the arm of the partition. And Macdonald, who introduced these notions, would draw his partition like this. So he called the leg the cells that would sit for him below, but for us above. So in French, legs, they point up. The arm of a cell, I'll call AC, and the leg of a cell, I'll call LC. So let's do rapidly an example. So if you want to calculate the, not arm and leg, but I mentioned the eigenvalues. So you fill the cells with the QT monomial. So this is Q to the 0, T to the 0, because this point here is 0, 0. And this is Q square, Q cube here you have t square, qt, and q squared t. So that's like giving a monomial name to the cell related to their coordinate of the cell. And then t mu is the product of all of these. So you will have t to the power 1, 2, 3. There are 3 t's here and 2. So you'll have t to the 5 and q to the 3 plus 2 plus 1, 6, 7, 8, 9, if I'm not wrong. So that would be T mu. And B mu, for sure, is just the sum of these guys. So if, by the way, if you, so it's clear that if you see B mu, you know exactly which partition you're talking about, because each monomial here occur once, and there's a monomial for each cell bijectively. So the set of B mu's is in bijective correspondence with partition, but if you're bored with what I'm saying, you can find the smallest example of 2 partitions that have the same T mu. So the set of T mu's does not characterize the partition. In terms of eigenvalues, that's going to come up later, the B mu's are all different. So the operator that we'll consider for this will have all its eigenvalues all different, but here you have repeated eigenvalues. Before we go on, let's talk a bit more about Macdonald polynomial. So a Macdonald polynomial has 2 parameters in it, qt, and infinitely many variables, x1, x2, blah, blah, blah. When you expand it in terms of the Schur, the first term is always Sn. So that's all the monomials of degree n in x. And at the end here, you have the elementary symmetric function in all the variables. And the coefficient here is precisely this T mu guy that we showed earlier. And in between, you have the other terms have coefficients which are sums of a few things. If you specialize both q and t to 1, then you get the same as calculating S1 x to the power n. So all mu's are the same when you set q and t equal to 1. If you go back to our example above, here, these coefficients become 2's and these become 1. So all 3 of these are the same when you set q equal t equal 1. If you switch q and t, and you remember my first 3 examples, then the partition here is replaced by the conjugate partition. This is a partition, this is the conjugate partition. So if you had, so switching the role of q and t does this. And if you replace q by 1 over q, t by 1 over t, now you won't have polynomials as coefficient, but you can multiply by something that will give you back polynomial. And the something by which you multiply is this guy, T mu qt, that I mentioned. And when you do this, you get almost the same as what you started with, but flipped like this. When I mean flipping, this is applying the operator, linear multiplicative operator on symmetric function omega that sends a Schur function to the Schur function indexed by the conjugate partition. So if you do this here, for instance, H31, you replace q by 1 over q. So this is going to be 1 over q squared, 1 over q, 1 over t. Here you'll get 1 over q squared, 1 over qt, and like that. And then, and this final guy would be 1 over q cubed t when you replace by 1 over both of the parameters by 1 over themselves. Now, if you want to make this polynomial turn back to be correct from the point of view having polynomial coefficient, you multiply everything by q cubed t. So this final guy will give you s 1, 2, 3, 4, and then you will have the first guy here will be q cubed t s 4, and then in between, let's do just one of them, you'll get, so here I'm multiplying what happens when I replace q by 1 over q and t by 1 over t here with q cubed t. And if I do it, what I get is precisely this guy here. So I'll get q cubed plus q squared t plus q t s31 plus other terms. And so you see, we get almost the same, in a sense, as what we started with, but flip like this. So the omega is going to replace this by this one, and so and all the rest like this, and you'll get back the polynomial. So that's another symmetry of Macdonald polynomial. I also want to mention that if you specialize one of the two parameters, they don't play the same role, but say specialize t to 1. Then there's something very nice that happens. These polynomials are not so complicated. They're the product of simple things. It's not the case above, but here, when you set t equal to 1, it becomes a product. And the product is over terms that are the same, but indexed by just one part, and with t equaled 1. But we already know that when h is indexed by only one part, t doesn't play a role. So I could have not written the t here. And so that's one of the Macdonald polynomial that we saw earlier, but I wrote it differently here. And if I know this, I can substitute above, multiply, and get the Macdonald polynomial specialized at t equals 1. Now, here, I'm using Plethism that I won't define today, but I'll tell you at least a special case here. So what this means is you take the symmetric polynomial here and you replace, so it has infinitely many variables in it, and you replace the first variable by x1, the second variable by qx1, the third variable by q square x1. You go like this up to infinity. Then you start again with qx2, qx2, q square x2. So the variables here are q to the I x sub j. And the reason, if you want, you can think of capital X as being the sum of the variable x1, x2 up to xj. So that's this sum here. Oops. And you have multiplied this by 1 over 1 minus q, but 1 over 1 minus q is the geometric series, and you expand it and you get this. Now look at this. In this series of all the monomials that occur, these are the ones that you see above here. So that's the what this guy is. Now, this is going to be an infinite series, but if you multiply it back by this factor, then everything simplifies and you get a finite expression. And we saw the case 3 earlier. So H4, using this kind of rule, would be calculated to be like this. And We can describe this explicitly many different ways. One of the way is just to, you take the ring of polynomial, you mod out by the ideal generated by symmetric function with no constant term, and look at, so the symmetric group acts on this. You decompose into irreducibles. Each green guy is an irreducible, and the q to the power something takes care of, reminds, or is going to encode the degree of the component. So this expression is the graded Frobenius transform of the character of this quotient. Okay. So now let me get closer to links, link homology and all this. So so I told you that the Schurs form a basis, the H form a basis. If you're asking yourself, what's the real definition of H's, go and look in the notes. It's not too complicated. An example is better to have in mind here than the specific definition, but if you want. So if I look at the change of basis in the opposite way, I express the Schur function in terms of the H's, then it's a bit messy at the beginning. So you get rational fraction expression, and these rational fraction expression have been involved in the description of the super polynomial in papers. And when we see these description, we know what they are immediately, because we've known this for 30 years, how this function, and we see the same formulas that we had 30 years ago about this. Now, in order to understand what's happening here, let me give you a formula, at least for the last guy here. So this one. There are such formula for others, but this one is very interesting and plays a crucial role in the story. So above you see S111. This is the same as the elementary symmetric function En, and it has apparently complicated coefficients, which are rational fractions. Now, these expressions, they are, so rational fractions like this, and McDonald essentially described what they are in original paper that he wrote. It was not stated exactly this way because there were change of normalization, but everything is essentially there. So the B mu that we saw earlier is here. And there's something else I'm going to tell you here, and something else here, and a parameter 1 minus 2, 1 minus q. So the change of basis that expresses the elementary symmetric function in terms of the h's as this format. The B mu is the same as before. And the P mu qt is like this. So it's still the product over all ij nu, but the 1 minus q to the t, q to the I, t to the j. But you have to be careful here, because if you include in this 0, 0, you'll get 0 out of this, and this is going to collapse. So I'm removing 0, 0 here. So so the numerator is the product of these two expressions, and then the denominator is a bit more complicated, but this is all in the story that with link homology. So it's a product over all cells of the partition, and you have here q to the length of the arm that famous arm that I mentioned earlier, and minus t to the leg plus 1. So that's a first factor. And then you have a second factor, t to the leg minus q to the arm plus 1. And so that's the numerator. So, so already in the literature, for instance, in this paper of Oblomkov, Rasmussen, Shady, and also with Gorski, there are expressions precisely like this with some other stuff. But the other stuff is normal, is something we understand, it just has to do with these operators that we're going to describe. And for instance, if you calculate it for the trefoil expression that you get what we mentioned earlier. Now I'll do a calculation. Still, I've not defined, I think, the operator nabla. I'm going to tell you how it works. So I mentioned that we start with this expression that I just mentioned. So this is sure 1, 1. I write it in terms of the h's. And then I apply nabla to this E2. The Macdonald polynomials are eigenfunctions, and their eigenvalue in this instance is q for h2 and t for h11. And where does this q come from? It's if you write h2 in terms of Schur's, remember that this was the t mu. And this also was the t mu. So I didn't show you the case 2 before, but that's how it is. And so when I apply nabla to h, what I'm doing is multiplying h by the coefficient that sits here. So that's the definition of nabla. Nabla applied to h mu is multiplying h mu by the coefficient, the last coefficient here before the S111. I'll state this again in a minute. So if I do this above, I'm multiplying by Q H2 and by T H11. And now, I mentioned earlier that the zero part of the polynomial, the super polynomial, it's zero part, it's degree zero part in the A parameter, is obtained by taking the scalar product of this with E2. Taking the scalar product means that I'm looking inside this H2 and I'm picking the coefficient of S11. Here, inside this H11, I'm picking the coefficient of S11 also. So from this to what we are looking for, what we do, oops, I'm gonna squeeze things. So the H2 here has been replaced by Q, the H11 has been replaced by T. I sum up these two and then divide by what's needed. Observe that here it's Q minus T and here T minus Q. So there's a sign here. And if you divide the two, you get Q plus T. So that's where Macdonald polynomial come into play. Now, that's Q plus T. Now I didn't tell you how to get A. And Jim Maglin, who was here at least earlier, I don't know if he's still, because
I'm still here.
Yeah, maybe Jim got bored because he knows all of this.
Oh, I'm here, Francois.
So then you wonder, what is the coefficient of A? Now, I'm telling you that you can get it from this. So this is S1. And now the coefficient of A is just take S1 and skew it. This is a symmetric function operator. Skew it with respect to E1. So EK skewing by EK means you have a partition, lots of rows, and you're allowed to remove one cell out of any out of rows, and you will have to remove, to get EK, you will remove one cell out of K rows. In each cell, you're not allowed to remove more than one cell. And you cannot do this if what you get out of it is not a partition. So the number of cell on each row must be decreasing. So that's the EK operator. So here in this instance, it works. So what's Macdonald eigenoperator in general are, so I mentioned earlier, they're operators on Macdonald polynomial with eigenvalues. These eigenvalues are some rational fraction expression in Qt or polynomial. And there are two basic operators at least, and more that are involved. There's the B operator, whose eigenvalue is B mu, and there's the nabla operator, whose eigenvalue is T mu. This is the sum of all the QITJ. This is the product of all QITJ. And in general, we will construct many other operators by constructing eigenvalues, taking the elements of this polynomial as the variable sitting inside a symmetric function. And these will be called FB. That would be the name of the operator here. So there's a link between the name of the operator and how to calculate the eigenvalues. Did I mention something more here? One operator that'll be very important is the operator for having eigenvalue operator with eigenvalue product of 1 plus a q to the I t to the j. Q to the I t to the j over ij. And this, essentially, it is this operator that constructs the Poincaré polynomial of triply graded Khovanov-Rosansky homology. So for the 3-4 torus knot that we saw at the beginning, you had this expression. Now, if you encode it in terms of Schur function, this part here is S3. So that's S3. So, and that S11, this is S2, this is S1, and this is S0. And now you can get everything from the first guy, which is S3 plus S11, by applying this operator E1. So E1 removes one cell in all possible ways along the rows of 3, and that will give you a S2. And if you remove in all possible ways one cell out of all possible ways to remove one cell here, you're just allowed to remove a cell in the second row because you couldn't do it in the first, and you get S1. So that's this term. Now, if you remove two cells in two different rows, here you get nothing because this is not possible. And here you get S0, which is 1 when you evaluate it. And that's this term here. So that's this expression down here. And let me maybe, so now, you might, so we need the first guy to start rolling, and then the other two terms, they fall out with the procedure. for the, I mentioned that this operator was really important. This operator is important. And so that's the operator, let's call it P, maybe PA. PA applied to H mu is doing this. And if you apply PA to En, and then apply nabla power k minus 1, you get Pn, Kn plus 1. So this special torus knot is just all explained using operators. And so if we want to understand other cases, then we need to expand our world. One direction is via elliptical algebra operators. And they have nice properties, for instance, with respect to conjugation to nabla and all that. And this gives you one technique to calculate the super polynomial with operators. And they are like, physicists like to call them creation operators, and also in the calculation of covariant homology, when you look at cobordism, there's this phenomena of creation when you look at, suddenly you have the unknot that appears. And so anyway, you have creation operators, you apply them to one, and you construct the symmetric function that is here. Forgot to write scalar product again. Some scalar product with E, say, N. And another direction is something that I've been working on for a while, but I might have something to say about this at some point. And now, next, we won't do this today. So this is just a scoop for next time, or one of the next time. Why combinatorics is because calculation of things like this have been, thanks a lot for work of Jim Haglund, have been described in terms of expression like this. So you count things with QT weight. And the things you count are subpartition of some staircase partition. So you look at, so this is a fixed staircase of some shape, Kn. The Kn that are here have to do with the knot. And you look at the diagonal of a rectangle of shape Kn, look at the largest partition that fits underneath the diagonal, and then count the partition that are contained in this staircase shape, and with some parameters. And one parameter is easy to describe. It's the area of the orange part here between the two paths. And the other is slightly trickier, but I'll try to explain to you why it is very natural another time. So I should stop here. Are there questions? And also, if I bored anyone that knows the subject, that's, as we mentioned in other presentation, that's a success, because I'm not supposed to unbore the specialist in the area. And if I wasn't clear enough, don't hesitate to, for instance, you wouldn't ask question today because you're too nice or too quiet or too distracted, but you can send them. And Nicole and I are working together on the notes. We want to make these notes understandable, and any of your question will help us fill up parts that might be missing in the notes.
I have a question which is a little bit of a tangent, but I thought maybe somebody here might have the answer. I've been curious about the Macdonald polynomials, not the modified ones, the p sub mu's.
The original.
Expanded in terms of the Shors.
Yeah.
Is that a totally naive question?
Oh,
Or is this written down?
It's you can get it from the H's using the yoga that passes from one to the other. I'm sure that it's written somewhere explicitly, but I tend not to look at them. So if you ask me, maybe Jim knows immediately, but
I could say a few things about it.
yeah, okay.
So first of all, it's a famous open problem to find a combinatorial formula for the Schur expansion of the H's.
Yeah.
But if you translate that problem into the P's, you're trying to expand the P's into what are called the plothistic Schurs, where you substitute a set of variables x by x times 1 minus t. So that's unknown, but a famous question. There's another question, though, you can ask. Can you expand the P's just in terms of the ordinary S's? And you're not going to get positive coefficients there, but I do have a conjecture. Essentially, if you specialize t to a power q and then divide by a certain power of 1 minus q, then you get a positive polynomial, but that's kind of unknown too.
Okay, thank you. It's one of these things that's so hard to do a literature search for because all the keywords are all in every paper.
Look, the way I do my search is I send a mail to Jim. For anything combinatorial, or if I have a conjecture, I send it to Jim before going on, because he's going to either say, oh, I don't know, which is a good sign, or he's going to say, oh, this is trivially comes out of my formula and this, and then he points out the paper.
I had one more comment. That's kind of a nice formula you get by taking the E1 perp of those things to get the Schroeder.
Yeah.
But I think I have a way of explaining that in terms of parking functions.
Yeah. It does.
I see. So you know that.
Yeah.
Okay. It's more complicated in terms of parking functions, but a little more general.
Yeah. So if there's no more question,
I have one more question.
Okay.
So in the formula that you have up there, is it known what the two statistics are?
This area and div.
But even for this generalized, like not under the staircase, but under a general partition?
Yeah, if you, yes, the short answer is yes, but I'll show examples where I don't know, because there's at some point you can generalize this even a little more. So the combinatorial, no, maybe no, the answer is yes. That's it. Yeah. For that part. There's Jim, the delta conjecture is hidden somewhere in what I said. And the analog of the delta conjecture for the whole situation, I don't know how it works. For the most general situation, that might come up at some point. But I don't even know if these correspond to actual polynomial PPT blah, 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 polynomial, super polynomial for special knots. So for torus links and knots, it's understood, but there are even more generalization. And then my question of the very beginning was, if I show you a polynomial in QTNA, can you tell me, oh, this is the super polynomial of a knot? I'm not asking you to tell me which knot. I'm just asking you, can this possibly be the Poincaré super polynomial for some knot? And so I can produce QTA polynomial written the way I mentioned, very naturally, but I don't know if they come from knots. Now, if you look in the table, like on Barnatan's site, you see a classification of knots. And with each knot, you can look up its covariant homology if it's there, and you can maybe calculate the Jones polynomial. But there's no reverse thing. So the reverse thing would be the following. I have a list of polynomial, and then I click on the polynomial. It tells me, oh, this is the polynomial, say the Jones polynomial, of at least these knots, potentially more, but at least. So I didn't see this. Arun what is the reverse pletism of, you see, I can't read the chat from where I am. So someone either.
I can read it. So Arun's asking, what is the reverse pletism of En, of the the elementary symmetric function, i.e. which symmetric function do I do the pletism of to get En?
I don't understand the question. What's the beginning point?
So to which symmetric function do you do a pletism of to get En as a result? I think that's, if I'm understanding.
En is a symmetric function.
But is it the plethistic modification of a different symmetric function? Arun, if you're there, maybe you can speak up, and maybe I'm not understanding your question either.
Pletism is often reversible, so I could write a long list of things. I don't know what.
Yeah, Nicole, you said it right, what I'm asking. But somehow you're in the transfer from McDonald's world to the H tilde world.
Yeah.
I take the P's or the J's to the H tildes.
Yeah.
Now, you are working in the H tilde world, and you're using En. So where did it come from?
Okay, so Jim more or less mentioned this when he talked about about this. So up to another renormalization, you have the P mu Q T X, and one of the first steps you do is to do Q T X 1 over T, and then something more, multiply and something. So, but the essential part is this pletism. So if you want to go to or did I write it the opposite way? Anyway, the pletism that is involved is this, or the reversed, which it would be this. Whoops. T, sorry. T. So these are the two pletisms that are essentially involved in going back and forth between the P's and the H's. So that's what you're looking for, Arun.
Okay, great, thank you.
Now, in one of the definition of the H tilde is via plethism like this and triangularity conditions. So it says that if you do this plethism, you get one triangularity. If you do the other plethism with Q, S mu x1 minus Q, you get another triangularity. Both triangularity and normalization factor, which is that the H tilde start with Sn, are sufficient to characterize the H tilde. So, so that would be the more technical answer to Arun's question.
There's another question. So Anne is asking if you have statistics for general lambda, and would this generalize the because it would generalize the combinatorial formulas for the generalized QT Catalan numbers in a paper of hers and Eugene's and other people.
Yeah. So every time you see the constant part with respect to the A polynomial, the A parameter in the expression that I showed earlier, that constant part is explicitly a generalization of the QT Catalan in various different ways. Most general definition would correspond to recent paper by Blazyak, Morse-Poon, Ayman, and Seelinger on where they're considering partition that sit below a line with any line, not only with points that are given by integers. If you want, this corresponds to this picture. So you consider so instead of a regular staircase, you consider partitions that are described by cutting with a line like this. And all the combinatorics of QT Catalan has been expanded to this, at least from the point of view of operators. There's lots of things to understand still.
I have something I might want to add to what Anne is saying about for general lambda. Is that general lambda instead of a staircase, you have a lambda? Is that what is being asked?
Oh, instead, if you want any lambda, so you were going to say something, Marino? I don't want to cut you off.
Yeah, because we do have a association for that with regards to the delta with the B operator, but only one statistic. So
yeah,
only a Q or a T, but no.
Yeah, the Q is not too complicated. It's the QT that is the fun story. But the QT here is very clear.
But we know actually what symmetric function that would correspond to as well. For the given lambda or something like that.
Yeah, but the other conjecture in the paper that I mentioned earlier, Blazyak, Ayman, and others, they have a conjecture about convex partition. So those that are cut by a convex curve like this, rather than just a line. And but the technology to calculate things there is along the lines of elliptical algebra and work of Feingen and Chimba. I will pronounce his name badly. So anyway, so there's algebras of operators and symmetric functions that are involved there, but that's another question I see from afar, or a comment by Andy, but I can't read from here.
Just a comment in response to what Anna was asking about like general lambda. I think some of the positoroid variety work goes a little bit further than convex, but I don't know if that's, I don't know 100% remember.
Okay. But I don't know how to relate all of the things that have been coming out with links. Maybe I'll do something naive now, but maybe it's so I mentioned that you have dick paths that go down and that are like this. Now, if you think of all of these squares as being just a copy of the torus, you identify both sides and the bottom and top. Then if you have a path that's going like this, up, up, and down, and like this, it's like, it's just drawing something on the knot, on the torus. And it seems, maybe some of the people in our gang know this, but it seemed somewhat natural to think that the calculation of homology has to do with understanding how all these paths behave. But this is very naive on my part. I don't know how to make sense out of this. Okay, any more questions? So the reason I can't read is I'm standing here. I have two screens far away. And when you do something in the chat, I see something occurring, but it's far away. And I don't wear my glasses.
It's okay. I got it.
Yeah, okay.
I'll read you the comments. Everyone.
So anything in the chat, I tell my students when I give my classes this way, please open your mic and talk. But that's a...
All right. If anyone has any more questions, let us know either now or through email. Otherwise, we're going to call it good for the day. And yeah, and I mean, I've said this a couple of times, but I'll reiterate. If you have any direction that you would like to expand upon, feel free to email us. We're happy to go in alternate directions as well. So,
another thing that is interesting, if you feel that you can tell part of the story, starting at, say, you say, oh, where Francois stopped, that would be natural for me to go on, then please feel totally free to send us an email and say, I'm ready to contribute in that part. I'm looking at a few people I know who could do that, but because this is a joint effort, where I can keep on talking if you want, but I don't want to monopolize everything. Okay.
All right.
So you'll get an email soon about next week.
Yeah.
Okay.
Next week, same hour, same link. Nothing will have changed.
Yeah.
All right. Thank you, Francois.
Thanks, Francois.
Thank you.
Thank you.
Bye.
Thanks for the talk.